This is a video solution walkthrough for the OCR A-Level Maths Integration Integral Topic Assessment. This is the pure Year 2. Question 1 asks us to find the area between these two curves. First finding the coordinates of the points of intersection. Fine, so to find the points of intersection, nothing unusual there. We just need to set the two expressions equal to each other and solve in the normal way. Divide everything by 2 there, factorise, and there are two results, x equals 2 and x equals minus 1. Just read the question again before we move on. Find the coordinates, it says, so we should give the y coordinates as well. And it's a good idea also to give your coordinate answers as coordinate pairs. Also, they're paired up nicely. It's easier for you to find them later if you need them in a later question. We don't here, as it happens. Now, part 2. You need to invoke the fact that the area between two curves is given by integrating the upper curve between the two x limits, subtract the lower curve, and by curve there I mean the expression for the curve, so y equals upper curve and y equals lower curve. You'll notice that instead of doing an integration subtract another integration, I've just integrated the whole subtraction. You can do that, and you should do that, because the whole thing simplifies and is a lot more efficient to do. Instead of doing two integrations separately, we can combine them both into one integration, like that, and you can trust that that will give you the result that you want. We just need to perform the integration in the normal way now and substitute. Instead of writing out the whole substitution here, that's fairly trivial, so I've just put ... and you should get 9 if you do that correctly, 9 square units. And that's our answer. Question 2. Okay, now we need to start thinking carefully about all the different integration methods that we have available to us. Now, those include integration by substitution, integration by parts, what I refer to as a Lun integral, or a perfect Lun integral, which we'll come to in a moment, and one or two other tips and tricks like using trigonometric substitutions and things, but it mainly boils down to using parts or substitution, or spotting that it's a perfect log integral, or Lun integral. So let's look at part 1 here. Is it an integration by parts? No, not really, because how would you split it up? You might attempt it and find that it seems to not simplify, or you just get stuck, and fine, you give up and you just have to try something else. But if you look closely, sorry, I'll tell you what, that's what I prepared earlier. Those are examples of where you might use integration by parts, but not necessarily. But it gives you a hint if you've got something like that. So that's why I said a second ago that it's not completely outlandish to think that part 1 here could be a parts integral, because it looks like this type here, x squared times something, but actually I don't think that's going to work very well. So let's press on. You might want to write it like this. Some people like to do this, some people don't. If you do write it like that, it does actually show you quite clearly, though, that we have a function of a function, i.e. here's a function in this bracket, and there's a function of that, because it's being raised to the power minus 2. And that's all being multiplied by a multiple of the derivative of the inside function. So the inside function is x cubed plus 2. Derivative of that is 3x squared, and look, there's an x squared out here. So if you have an integral of this form, a function of a function multiplied by the derivative of the inside function, that screams substitution. So we're going to do a substitution, and the substitution you should use is u equals the inside function, in this case x cubed plus 2. If we go through the motions now, before you go near the integral, make sure you differentiate and get dx in terms of du. And then you can go to your integral and write things out. So the x squared at the moment we're just going to leave there. We're dividing no longer by that complicated thing, but just u squared. But instead of dx, we've got du over 3x squared. And of course, the x squareds cancel. I'm going to move that third, the du over 3, I'm going to move that divide by 3 outside the front of the integral there, just to keep it out of the way. And we end up wanting to integrate just 1 over u squared du, which is easily done. And don't forget to substitute for x again at the end. That's it. Now part 2. Now remember, before I said you're either dealing with parts substitution or a perfect log integral. This is a perfect log integral. Now something I forgot to mention in part 1 is if you're dealing with a fraction, if you're integrating a fraction, like both of these are, the first thing you should look for is to ask yourself, is the numerator the derivative of the denominator? Or is the numerator a scalar multiple of the derivative of the denominator? Now in the first case, if that squared wasn't there, then this would work, because the denominator's derivative is 3x squared and there's an x squared on top, so you could make that into a perfect log integral. But the squared stuffs it up. But that's not the case here. It doesn't stuff it up at all, it's perfect. If you differentiate the denominator, you get the numerator perfectly. So we don't need to do anything clever. It's just that. Now note that either of those two results pictured there are fine. You should really use absolute value brackets if a ln arises as a result of integrating. But in this case you'll notice hopefully that 1 plus e to the x can never be negative anyway, so there's no point in having those absolute value brackets, just use normal brackets. Okay. So question 3. Is it parts, is it substitution, is it a perfect log integral? Well, it's not even a fraction, so it's not a perfect log integral. So let's consider substitution or parts. Well, it looks like it could be parts because we've got x times a function of x. Well, that looks like it might be parts because you differentiate the x, but then if you try to integrate the e to the power x squared, you'll find that you cannot integrate that. It's actually impossible to integrate that. So you could start doing parts and then get stuck and then think, okay, that's fine, I'll just now try substitution and sort of either cross that out or just move on. This does require you to do a substitution. Now, here's another way of writing this integrand. So what I've done there, instead of writing e to the power something, I've just sort of defined this new function, exp, which does e to the power of whatever's in the bracket. And if you write it like that, you could think of it as not dissimilar from doing something like x sine x squared. And here we have a function of a function, so x squared, and then a function of that is sine of that, times the derivative of the inside function. The inside function's derivative is, of course, 2x, and here is that x. The 2 sort of will take care of itself. So function of a function times by the derivative of the inside function screams, as we said before, substitution. So let's do a substitution of the inside function, go through the motions, dx in terms of du, and then the integral becomes that. Now that x there lurking is going to cancel with the one under the du. I'm going to move the du over 2, that over 2 can come out the front of the integral again, and we just integrate e to the u du. Now notice that the limits have to change, because we've changed from x to u, and we're just going to integrate with u now. All the x's are just gone, we don't care about those ever again, but don't forget to change the limits into u limits, and then just integrate as normal, put your new limits on, stick them in, and get your answer. Don't go typing that into the calculator and pressing SD button. That's not helpful. At this level, they will ask you to find the exact value of. So we leave it like that. Okay, part 2. What do we do when it's a fraction? We ask ourselves the question, is the numerator the derivative of the denominator? Yes, it is. It's a perfect ln integral. So the answer is just ln of the denominator. Do we need absolute value brackets? Well, sine x is between minus 1 and 1. Well, sine x plus 1 is between 0 and 2, so it can never be negative, so again we don't need the absolute value brackets. And then we need to evaluate that between pi over 2 and 0, stick the limits through, and we get that. Ln of 1 is 0, so we just get ln of 2. Part 3. Now, here's another little trick to help spot what we're dealing with here. If you write, I've never been a fan of this notation here because I think it hides things. I can understand why we use it because it stops you having to need so many brackets. But if you actually write those brackets in and write it like this, you can see that we have a function of a function multiplied by the derivative of the inside function, which screams substitution. So u equals the inside function, go through the motions, okay, at this stage the cos x's will cancel, don't forget your new limits. And it's pretty easy from there. We get our answer, which is just a third. Okay, questions 4 and 5 are quite different. Again, you might look at question 4 and think, aha, it's x times a function of x, so that might be parts. Well, you can actually do this by parts, but I wouldn't recommend it because you have to you'd have to differentiate the x and integrate this square root of 1 minus x. You can do that, but you have to use reverse chain rule to integrate that, and you're then using reverse chain rule within an integration by parts, and yeah, that's just going to get hard and error prone. So in this case, a substitution works perfectly fine. If you do u equals the inside function, again we've got a function of a function. Okay, it isn't multiplied by the derivative of the inside function this time. We'd have to have a minus 1 there, wouldn't we? But it still works actually, this one. So we press on and just go for it. So go through the motions, differentiate the substitution. In this case, du equals minus dx. And then when we substitute things in there, keep the x the same, that's that x there. Integral of, square root of u, and then times don't just write minus du, because I know you know what that means, but it's times minus du. That minus really wants to go out the front of the integral, out the way. Now don't forget also to do your new limits. Now when you calculate your new limits here for u, they look like they're the wrong way round, but that's okay, just leave them where they are, trust that for now. You can still trust that they'll behave the way they're expected to behave. Now to deal with the x this time, it doesn't cancel with anything, so we're going to have to rearrange our substitution. And when you do that and substitute it in, I've put the minus out the front as I said I would. New limits there. And the x is now 1 minus u, and we're timesing that by the square root of u, which I'll write as u to the half. And we've got du. Now here's a little trick. When you've got the limits kind of upside down, the wrong way round, and you've got a minus out the front, you can get rid of the minus here and swap the limits over. That always works. And I'm in the same process, I've done that now, I've got rid of the minus and I've swapped the limits over just to make things a bit easier for myself. And I'm going to expand the brackets now, so 1 times, that 1 times u to the half gives us u to the half, and that minus u times u to the half gives us minus u to the power 3 over 2. Great, it's pretty straightforward from there, just normal integration. I'll just move up here out of the way. Normal integration, put your limits through, and we just get 2/3, take away 2/15. Sorry, let's go back to that. Press the wrong button there. 2/3 minus 2/5, and we get 4/15, which is the final correct answer. Okay, question 5. I'll start up there where I've got plenty of space. This, you need to learn that if you have a ln x as part of your integrand, then you need to use integration by parts. That's just a fact you need to learn. So once you've established that it's parts, it's just go through the motions of parts. So you're going to have to differentiate the ln x, because integrating that will make it more complicated. And we're going to integrate the 1 over x squared to get minus... Oh, if you think of that as x to the power minus 2, it's easier to integrate. And we get minus 1 over x. Get your formula book, make sure that you substitute these in correctly. So that integral there is going to become minus 1 over x ln x. Subtract the integral of minus 1 over x squared. That's coming from this times this. So du dx times v. Let's just simplify that. I'm just going to get rid of those two minuses, cancel to make a plus. And then we can just integrate as normal on the right. We've actually already integrated that expression before, haven't we? So we know what the answer to that is. Now, don't forget to put your limits through. Remember to always look back at the question before you move on. Put your limits through, and we get this awkward-looking expression, which simplifies quite a lot, actually. Ln e is just 1, and ln of 1 is nothing. So we just got a plus 1 there. So final answer, 1 minus 2 over e. Okay, question 6. Right, we've got x times a function of x. This is parts. Okay, this time it really is parts. So you're going to... do you remember when we looked at this one before? This turned out not to be parts. We actually did a substitution with this one. Now this one looks like it might be the same, but it isn't. This one will yield to parts. This is why experience is so important with these in practice, because otherwise how do you know really which one it's going to yield to? And very rarely do they yield to more than one method. So we're going to set this up with parts. Well, hang on, this is... I'll tell you what I'm doing here. I'm actually trying to do a substitution. This is what happens if we do a substitution. It looks like it might work with that previous one. Let's go back to this. In this case, substitution worked. We did u equals this inside function and it yielded. But if you do that here and use u equals 3x, you find it just doesn't work. At some point we're going to get stuck here. Let's see what happens. So u equals 3x. I've differentiated to get dx in terms of du. And we end up with x sine u, and then dx, which we'll write as du over 3. But what now? Because we're going to rearrange up here, we're going to rearrange x to the substitution to get x in terms of u. And we end up with u over 3 sine u du over 3, which if you wanted you could write as a ninth of u sine u. But now we're still stuck, because how do you integrate u sine u? We haven't really made any progress at all. So this is parts. So parts, we're going to differentiate the x. We're going to integrate the sine 3x. Don't forget the sine integrates to minus cos. So we've got minus the third cos 3x by reverse chain rule. Put everything in the formula. Then we've got minus times a minus there, which I'm just going to tweak it on that same line. And then we've got to integrate again on the second term. And that's it. So once you've spotted its parts, look, we've got effectively 3 lines working there. Question 7. So expressing partial fractions, well, this... we know it's going to end up looking like this. And when you've got, don't always use this, but when you've got a simple, what I call a simple denominator, so non-repeated factors, so there's no squareds after the brackets, no squareds there, and linear factors, so linear non-repeated factors, just like this one, so no squareds anywhere. If it's like that, you can use this thing called the cover-up rule. So we're going to think, what goes here above the x plus 1? Well, first think, what number x for x will make this expression here 0? Obviously, minus 1. So cover up that factor in the denominator in the original expression and substitute your minus 1 in here. So minus 1 divided by 1 gives us minus 1, and that tells us what to put on the top of that. For the second, to work out what goes here, think what value of x makes this 0, minus 2. And we're going to substitute that in, again, just cover up this one this time, and substitute minus 2 in here. Minus 2 divided by minus 1 gives us 2. A quick way of doing those ones. Okay, so we're going to integrate that between those two limits. Now, a good trick with this is to split it into two separate integrations, so they don't interfere with each other. You don't have to do that, but it's recommended. Oops, I've done it again. Let's come back a bit to there. Okay, we can the first one is a perfect Lund integral, so we need the minus at the front, but we've just got log of x plus 1. We don't really need those absolute value brackets because the numbers we're going to substitute mean that it won't be negative anyway, but force of habit, I'm going to put them in. With the second one, now what you can do with this awkwardly is to go, well, is it a perfect Lund integral? Almost, not quite. The derivative of the denominator is 1, but we've got a 2 there. So to make that a 1, we'd have to multiply by a half, and to compensate for that, we'd have to divide by a half outside, or times by 2. But I think it's easier just to think, instead, let's just move that 2 there out the front, like we're factorising it out, like we've done really with this minus here, putting it out the front of that integral. So I'm just going to stick that 2 there on the same line. Great, now we've got a perfect Lund integral, so we've got two lots of log of x plus 2 with those two limits. Let's move up here for a bit more space, put your limits through, and we get this funny looking expression. I don't leave it like that, simplify, so I'm going to expand the brackets. Ln of 1 is 0. So 2 ln 4 minus 2 ln 2. Now to combine those into a single logarithm, let's move those 2's up to be powers. And then combine into a single logarithm as so. And simplify. Ln of 4/3, final answer. And question 8, final one. All we need to do here for part 1 is, again, think about the different methods we've got. Is it parts? It might be, but probably not. Is it a function of a function situation? Yes, it is. So you might want to write it like this, and then it becomes really clear that you've got a function of a function, and the derivative of the inside function, which is 2x, is sitting there. Don't worry about the 2, but the x is there, and it's going to cancel when you do a substitution. So your substitution is the inside function. Go through the motions, substitute everything into the integral, and cancel the x's. We've got a nice, easy integral now. I've moved the half outside, and we get that thing there, which is, substitute the x's back in, we get this. But it might be a good idea to, if you're probably in the exam going to need to use this in a later calculation, so it might be better to write it in fraction form. And part 2. There's a few different ways of doing these. Here's one. You can, it's partial fractions, so you can spot that it's an improper fraction, and you can therefore write it as a plus b over x minus 1 for some integer values a and b. And if you work those out, you will get that a is 1 and b is minus 1. And then you've got something that you can integrate pretty straightforwardly. But actually, this one just yields to substitution. So try it. If you're unsure, substitution is normally the one. Okay, that's my big tip. If you do u equals that thing on the denominator, because if you think about it, the problem is dividing by x minus 1 is weird. Dividing by u is going to be nice. So let's make that happen. In this case, du dx is 1, so du is equivalent to dx. There's nothing wrong with splitting the derivative like that, du equals dx. a professor of maths might be annoyed at me doing that, but this is A-level and you can get away with it, so just make things easier for yourself by treating them like normal fractions. Right, when we substitute things in, we get x over u du. But that x can be from here taken, we can rearrange the substitution to get x equals u minus 1. So we're integrating u minus 1 over u du, which can be written 1 minus 1 over u du. Cast your mind back to those red partial fractions I had a moment ago, which look very similar to what you're looking at right now here. Integrate that, u minus ln u, I should have a plus c there, and then replace with your expression for x. And you've got your answer. It is actually possible at that stage. Notice you've got x minus 1, so that minus 1 there, and the plus c, effectively we've got x, take away ln of x minus 1, plus c take away 1, if I move that over here. Now you can redefine c take away 1 as k, or just redefine it again as a new c if you want. So really we don't need that minus 1, but it's not a problem being there, and you would never lose any marks for leaving it there. And that's it.